Hi, this is Dr. Asan Abdullah with the course Deep Reinforcement Learning. And the topic which we are covering is reinforcement learning. And this is the 10th topic in the list of topics which are covered in this course. And the subtopic is A. So this is lecture number 10A. So its difficulty level of this video is basic or easy. And the supplemental website which is used for this lecture is the easymcq.com/goget, which is a personalized learning management system. So, what is the future of content delivery? So, the future of content delivery is delivering the content online, and the wonderful features and the benefits are in front of you. And this approach is used by hundreds and tens of millions of users worldwide, which use content delivery for the learning purposes, for education purposes. And we are going to be following the same approach in this course also. So, in green color is the URL for the personalized learning management system, and in blue color are the videos which explain the features of the personalized learning management system with reference to the future of content delivery, which is, as a matter of fact, the present. So, what it supports is advanced and basic text search in the content of the course coverage, which is not there in very popular learning management systems. And then, of course, if there are any students with visual disabilities, they can also change the font, the color, the line spacing, etc., to suit them to their requirements, which is also not there in leading learning management systems. And then all the content is kind of opens up and unrolls so as to optimize the small screen of a handheld smart device. And you can also track your progress, what you have covered, what you have to cover. And of course, you can also test yourself online in real time about the knowledge assimilation and the knowledge which you have acquired, and the weaknesses are also identified. So, what is the approach of content delivery? So, there are two approaches. One is the question and answer based, which is proactive, which is engaging, and which is also promotes thinking also. And the other approach is the traditional approach in which a lot of details are provided. So, the approach we have adopted is a blend of both approaches, that is Q&A and traditional learning also. So this is the list of topics which are covered in this course, and we are at topic number 10, which is reinforcement learning. So this is the breakdown of the list of subtopics or the concepts which are covered in this video or in this sets or series of videos. So 10A in yellow color are the basic or the fundamental concepts of reinforcement learning. And as we proceed from A to B and so on up to E, the difficulty increases progressively. And for the video lecture 10E, we have the more challenging concepts. And now we move on to the details of the video. So we start with lecture 10A, which is reinforcement learning. So, what are heuristic search algorithms and their key characteristics? Well, heuristic is like something, a rule of thumb or educated guess, or the algorithms which make an estimate about the quality of the solution or the quality of the path to be adopted in a search space instead of following a brute force approach. So these techniques are used in AI and other domains also for computationally and intractable problems. So why they are attractive? Because heuristic search algorithms they offer efficient and flexible and approximate solutions. Okay, and for of course by and they reduce the search space and the search processes. So basically, what the heuristic search algorithms do is that they kind of balance the performance and practicality, right? Especially for brute force techniques as an alternate to the brute force technique. So they deliver good enough solutions, which of course are faster than exhaustive methods. But remember that as opposed to an algorithm where there's a 100% guarantee of correctness and optimality, we don't have these guarantees for heuristics. So, for example, they're effective and for structured environments. So, for example, where the domain knowledge can be included in the heuristic function. For example, like A star algorithm or simulated annealing. So in simulated annealing, what we are doing is that we are trying to mimic the annealing process of forging metal alloys. And then is the beam search. There are other techniques also. Now, the heuristic search algorithms are not central to deep learning, or they're not central to reinforcement learning also, but they are increasingly integrated into hybrid frameworks. Why? Because they assist in planning, they assist in exploration, and they assist in pruning the search space, or pruning the action pruning. Now, one has to be able to understand the characteristics of these heuristic algorithms and their use cases also. Then they can be correctly and effectively employed and used. So the example which is on your it is on the screen. So we have the feasible solutions here on the x-axis, and we have the cost function. So the objective is to reach the global minimum. This is the global minimum, and we have number of local minima also, and there's a good chance of getting stuck in the local minima. So the only way to get out of the local minima is to follow a hill climbing approach. This is hill climbing. So this is the initial solution. So now the question arises that how often this hill climbing should be done, and with which probability. So so the classical example is simulated annealing. So what happens in simulated annealing is that the hill climbing takes place with a certain probability. Okay, and there's a concept of temperature. So that parameter temperature controls the likelihood of whether to accept this worst solution, which basically degrades the objective function which was required to be minimum. And the objective is that to avoid getting stuck in this local minimum, because if it gets stuck there, then it won't be able to reach the global minimum. So if a new solution is better, obviously it is accepted. But if so this new solution is better, accept, and we go this over here. But if it's worse, because moving ahead, so to say, will worsen the solution, then it's accepted with a certain probability that depends upon the temperature parameter. And that higher that temperature parameter, the more likelihood of that worse solution being accepted. But what happens is that that temperature parameter gradually decreases over time. So this bad move of hill climbing is less likely to be accepted over the period of time. So this is how simulated annealing is implemented. So what we have here is, say for example, the key characteristics are efficiency. So what is meant by efficiency here? Efficiency in search, because what happens is that the performance gets improved by guiding the search towards promising areas of the solution space. This is what we have as the solution space, and this is done using heuristics. So there's no guarantee, but there's a likelihood of better solution for exhaustive alternatives. So this basically approach of this reduces the unnecessary exploration, which takes time and resources, and that significantly speeds up, improves the problem solving capability in complex environments, in large environments, instead of using the brute force approach. So that is the objective or achievable. So approximation. So heuristics also provide approximate solutions. Now, approximate solution basically in the context of approximation algorithms. Okay. Why? Because when the exact answers are computationally very expensive and they are not feasible. So what happens is that heuristics sacrifice the guarantee of the algorithm, sacrifice the optimality, and trade off with practical results, with realistic results, which are useful but they are not optimal. So that makes them suitable for real world problems. Which kind of real world problems? Problems where near optimal solutions are acceptable, and where the resource in terms of time and computational power is limited. So domain knowledge utilized. Now these heuristic algorithms, they depend heavily on domain specific knowledge, which is encoded in the heuristic function, like in simulated annealing, okay, like in A star algorithm, like in beam search. So that knowledge has to be there, and this knowledge influences the decision making during the search process. So this knowledge, so this is the search kind of process here. So that helps the algorithm estimate uh, the, the best path or action based upon the problem specific cues. Based upon the problem specific cues. That can help, but that requires domain knowledge also. And then is the flexibility in design. So these heuristic search algorithms are highly adaptable across not all domains, across certain domains. And the objective functions are developed in such a way that they can be fine tuned or they can be modified for various types of problems. For example, the problem could be pathfinding, the problem could be scheduling, right? So what they do is that these heuristic algorithms, just a moment. So these heuristic algorithms, so those parameters are adjusted or they are combined with other optimization strategies. So some of the examples of these algorithms, say for example, is the A star pathfinding heuristic. A star. So this is the classical AI algorithm. So it uses both the actual cost and the estimated cost to reach the goal. So it is very it provides very good results and even optimal results, and it can complete when using an admissible heuristic. Okay, and of course they are widely used in pathfinding and algorithms and scenarios where the problem can be uh, represented in the form of graph, and we have to perform the graph traversal. Then is the greedy best first search. So basically this algorithm is a greedy algorithm and always selects a path that appears to lead uh, directly to the goal. So this is solely based on heuristic estimates. It is fast. It is fast, but it is not guaranteed. It is fast, but it is not guaranteed to find the optimal solution because it is greedy. So in that effort for greed, it may like avoid those apparently costly paths which result in global optima being achieved. Simulated annealing we've already discussed. Then is the genetic algorithms. So basically, they simulate the natural selection process. So we start with a certain population of solutions which evolved over generations. So it's very slow, and then we mimic the operations like mutation and crossover, which basically help explore the search space, okay, and optimize the performance across complex search spaces and search spaces that are non-linear, okay. And then is the beam search. So beam search pruning, that they offer this search offers a fixed number of top candidates. So this is again a greedy approach because a candidate which may not uh, come in the list might lead to a better solution. And then there are heuristic scores also. So that kind of balances the efficiency and accuracy, and is of course used in certain applications such as natural language processing. All right. So if you are interested, you should be. So these are all the details. Okay. Much more, lot of details are here, and here are the references if you would like to move ahead. All right. So when do the heuristic now heuristic search algorithms are used, right? Why they are used? Because they work under certain scenarios, they work good under certain situations. So when heuristic search algorithms work well, they work well. Re- Remember one thing, that working well does not means optimal solutions. Optimality is something totally different. So when we have large problem spaces, we'll talk more about it. So for large problem spaces, brute force techniques, they are very expensive, and they work well when it is not possible to timely get the exact solutions, or it is very expensive to get the exact solutions. It's not practical also. So the objective function or the time complexity is non-polynomial, which is discussed in algorithm analysis, and so on. So, in a nutshell, these heuristic search algorithms excel when the problem domain possesses a structure. or there is domain knowledge also. We'll discuss those details, and that knowledge can be encoded in guiding the heuristic, especially for avoiding exhaustive search. Okay, so so in deep reinforcement learning and hybrid systems, heuristics serve as planning or guidance modules. They prune the search space. They propose candidate paths. They are used to solve sub problems. So what they do in a nutshell is that they help the agents scale to meet the complexity of the complex environment, and they reduce the sample and the computational burdens also. All right. So and of course they are more effective. As a matter of fact, they are most effective in domains where the option is brute force or exhaustive search, which is computationally infeasible. Okay, but for example, guided search can help. So in deep reinforcement learning or hybrid planning or learning systems, heuristics can help when the agent must plan or explore within a large or structured subspaces. Okay, so these are some of the domains, and especially when dealing with imperfect or incomplete information. For example, in partially observable environments, heuristics can be used to estimate the missing or uncertain component to guide decision making, okay, in place of full knowledge. So, for example, optimization problems like resource allocation or scheduling or function minimization, they also benefit. So, in a nutshell, these heuristics help navigate complex objective landscapes by guiding the search. Okay, so what? Let's go into those details of these bullets. So, large problem spaces. So, in scenarios where the state or action space is extremely large, okay, it could be combinatorial or continuous, and exploring every possibility is infeasible. So, in that kind of environment, heuristic search algorithms excel because they prioritize promising branches, and they kind of do not explore or prune away less useful regions. But that can also be act like a double-edged sword also. So that effectively reduces the search space. For example, robot planning and so on. And the scenario where the exact solutions are impractical also. Now, heuristic search algorithms also work well uh, even when conceptually simple problems become intractable due to the requirements of memory or time constraints. So, in such cases, it is not realistic to compute the exact solution. So, therefore, in such scenarios, heuristics provide fast and approximate answers, okay, which are acceptable under those constraints. For example, consider A star algorithm with an admissible heuristic that can deliver near optimal paths faster than the Dijkstra's algorithm. Now, in deep reinforcement learning, when we are planning simulations or proposing certain sequences of actions, uh, heuristics approximate, they're costly, okay, under time, under tight time budgets. So we would like to go with a certain cost and with the loss of optimality also. Then no polynomial time. Okay. So we have like NP hard problems like the traveling salesperson problem or the graph partitioning problem or the graph coloring problem and so on. So they lack polynomial time solutions. Now, and those exact algorithms, they don't scale well for large problems. So there's no other option than to go for heuristic algorithms. Now, these methods, they are smart techniques, but they are not exact. So what they do is that they sample the search space or explore the solution space, okay, using random or simulated strategies, okay, which are guided by heuristics. So what they are trying to achieve is that instead of a non-polynomial approach or a brute force approach, they achieve a middle ground. Now, while this does not guarantees optimality, but but they do deliver strong and approximate solutions efficiently with efficient use of resources. Now, in reinforcement learning systems, they which embed like planning or resource allocation tasks, heuristic sub solvers or sub algorithms enable practical solutions where the exact solutions are not feasible. Okay, so let's move ahead. So move ahead to imperfect information. Imperfect information. Okay. So when the agents come across incomplete or noisy or partially observable environments, heuristics can help, and they can help uh, to approximate the unknown states or transitions that guide in decision making. Now, say for example, in a partially observable world, uh, we estimate the rewards or penalties that can guide the planning towards better solutions. Now, in deep reinforcement learning, heuristics support exploration by estimating the likely state values because of this imperfect information. Now, this adaptability makes the heuristic search valuable in real world scenarios with uncertainty in the domains. Optimization problems. So consider tasks like scheduling or resource allocation or hyperparameter tuning, uh, which is complex for large and non-differentiable search spaces. For such scenarios, heuristic methods like genetic algorithms, simulated annealing, taboo search, etc., they are well suited. Okay, because what they do is that they balance exploration and exploitation. Now, in deep reinforcement learning, these methods support meta optimization. That is, they allow fine tuning architectures. Okay, and so where gradient based techniques fall short, that's a reality. So, the heuristics allow efficient navigation in high dimensional spaces where traditional methods fail. So, that is why they are used successfully. Pathfinding and navigation. Now, pathfinding is a classical heuristic domain. Okay, we have the moving agents from start to goal in space. So, if there is a grid environment or continuous environment, then heuristics like Euclidean or Manhattan distance can guide efficient search. And algorithms like A star use these search results to find shorter paths quickly. How? By combining actual and estimated costs. So understand that without heuristics, such systems would require excessive exploration and which kind of undermines the real time performance or the real time requirements. And finally, the constraint satisfaction problems. So these problems involves assigning values to variables under constraint. Example like scheduling or satisfiability problem. So the search spaces grow rapidly, and like brute force backtracking becomes unmanageable. So in these scenarios, heuristics improve feasibility by guiding the value variable, by ordering, okay, by pruning the branches early, and by applying the constraints. So strategies like most constrained variable or least constraining value, they significantly reduce branching. So in reinforcement learning systems involving symbolic or resource planning, heuristics solvers prevent the what is called as the combinatorial explosion. Okay, so if you look at this graph over here, so if you start from A, so we have the option of going to B, C, D, and E. So from we have the option B, C, D, C, D, and E with certain costs. Now, when we explore them, okay, then we have other options. So we see that if you start from A and visit all the vertices and return to A, so this one cost is 375 units. This cost could be 425 units. Of course, we are interested in the least cost. So this is how the traveling salesman person problem works. So this is very computationally intensive because we are looking at n factorial possibilities which is non-polynomial polynomial and can be approximated by n power n.